Okay, so now let's put this in action. Okay, so we have a 3 by 3 matrix, calling it A. Big surprise, I do that all the time, but anyway, we're going to calculate its determinant using cofactor expansion along the first column. Now, is that the only choice? No. There's 3 different rows. We could have picked any row to do cofactor expansion along, or there's 3 columns. We could have chosen any of those columns to do cofactor expansion along. But in this example, it says we're going to use cofactor expansion along the first column. Okay, before I fill this in, let's just jump back to this formula here. So what are we looking at? We're looking at cofactor expansion along a column down here. So we're looking at this formula with j equal to 1 because we're choosing the first column, right? So the first thing I'm going to do is I'm going to write down this expression here, but I'm going to write, instead of j, I'm going to write 1. And then of course, instead of n, you know what I'm going to write? I'm going to write a 3 because this is a 3 by 3 matrix. Okay, so that's how we're going to start this. So we'll write determinant of A is going to be equal to the sum from k equals 1 to 3, and then we're going to take the entry from A, which is in the kth row and the first column, and multiply it by the corresponding cofactor. Okay, so again, all this is, I've just applied this formula with n equal to 3 and j equal to 1. And then, of course, we're going to expand it out next in the next line. But let's do that here. Okay, so for when k is equal to 1, we're going to get the entry from A in the first row, first column, multiplied by the corresponding cofactor. Then now plug in k equals 2. We'll get the entry from A in the second row, first column, and multiplied by the corresponding cofactor. And then we'll do the same thing for the entry in A in the third row, first column, and multiplied by the corresponding cofactor. Okay, so that's our first step. We just expanded the sum. Okay, well, what's this going to look like? Well, let's plug everything in. So A11, that's the entry from the matrix A in the first row, first column, so that's a 3. So we've got 3, and then what is C11? Remember the formula for cofactor? I'll just pull it out over here. Remember, so we were using this formula. C11 is negative 1 to the 1 plus 1 times M11. We're just going to use this formula here. So that's to evaluate this cofactor here. So negative 1 to the 1 plus 1 times M11. So that's our C11 that we just evaluated. Okay, so that's the first term. Now the second term, we're going to have the entry from A in the second row, first column. So that's going to be negative 2. And then multiplied by C21. So that's going to be negative 1 to the power of 2 plus 1 multiplied by the minor in the second row, first column. All right, and that's our second term. So now our third term is going to be A31. So that'll be the entry in A that's in the third row, first column, which is a 5. And then what do we have? We'll have negative 1 to the power of 3 plus 1 times the minor corresponding to the third row in the first column. Okay, finally. So now all we've done is we replaced all of these 3 entries with the actual numbers from the matrix. So notice that the coefficients here of these big blocks, I've got 3, negative 2, and 5. That's exactly the entries in the first column there, right? Which makes sense. We're using cofactor expansion along the first column. Okay, and then what else do we have? Well, what else can we simplify? Well, let's do all these powers of negative 1. That's fairly straightforward, right? Negative 1 to the power of 1 plus 1, that's negative 1 squared, which is just positive 1. Here we've got negative 1 to the power of 2 plus 1, so that's negative 1 cubed, which is an odd power of negative 1, so it's going to be negative 1. And then here we have another even power of negative 1, negative 1 to the power of 4. So this is going to be equal to positive 1. All right, so now what happens? Well, let's write this down. We're going to have 3, this 3 times 1, so that's going to be the 3. Now M11, what's M11 again? Remember, that's the determinant of what is left from the matrix A when you delete the first row and the first column. So this M11, just delete the first row and the first column, and what are you going to be left with? This bottom chunk down here, negative 4, 3, and 4, negative 2. So we're going to have times the determinant of those 4 entries. So negative 4, 3, and 4, negative 2. Okay, now what about the next term? Well, we've got a negative 2 here. This power of negative 1 turned into a negative 1. So we've got negative 2 times negative 1. That's going to result in a positive 2. Now plus 2. And then we'll have this minor still as well in this for the second row and first column. So we're going to have the determinant of the matrix A after you were to delete the second row in the first column. So you're going to delete the second row and the first column. So you're going to have the 1, 2, 4, and negative 2. Pardon me, 1, 0, 4, and negative 2. Okay, now what's next? This last term, right? You'll have negative 1 to the power of 3 plus 1. This turned into 1, so we got 5 times 1. So plus 5, and then this minor here, the minor in the third row, first column. So that's going to be what you get from the matrix A. You're going to delete the third row and the first column, and then take its determinant. You're going to get 1, 0, negative 4, and 3. Okay, so now we need to just work out these 3 smaller determinants, and we're almost done. So what's going to happen here? This is going to be 3 times what? Negative 4 times negative 2 minus 3 times 4. So that's the first determinant. And then here we're going to have plus 2. The determinant here will be 1 times negative 2 minus 0 times 4. And then for this 2 by 2 determinant, we're going to have the 5 that's on the outside. So we'll have 1 times 3 minus 0 times negative 4. Really, don't forget what I'm doing here, right? Remember the formula for a determinant of a 2 by 2 matrix? It's the one we gave right at the very beginning of the section, right? You can go multiply the entries on the main diagonal and subtract the product of the other 2 entries. So we're using this rule here to calculate the determinant of these 3 2 by 2 matrices. Okay, so we're almost done. What does this evaluate to? So this will be 3 times what's inside the bracket, negative 4 times negative 2, that's going to be positive 8. But then we're going to subtract 3 times 4, which is 12, so it's going to be 8 minus 4, or 8 minus 12, which is negative 4. And then here, what do we have? In the next pair of brackets, I'll write the 2 down. So 1 times negative 2 minus 0 times 4, so that's just going to be negative 2. Okay, and then over here we'll have plus 5. This will be 3 minus 0 times negative 4, so that'll just be 3. Right, okay, so finally, what do we have? 3 times negative 4 is negative 12. Minus, this is going to be negative 4. So we've got negative 12 minus 4, which is negative 16. Then we're going to add 3 times 5, which is 15. So that's actually going to work out to negative 1. So finally, we got our answer. We got the result. That is the determinant of this 3 by 3 matrix up here. Okay, so that is the key. So that was cofactor expansion was the key to getting that at this point. Okay, so it is a lot of notation at this stage if you're just carefully unwinding the formula and following it carefully. But it turns out there's a few things you can do to streamline this process. And as you get more and more practice, you start to recognize patterns and you can cut down on some of this notation. And that's what the next few remarks are going to discuss. And then afterwards, we'll see an example of how we can do this in a bit more of an efficient way. Okay, the first remark I want to make is this factor of negative 1 to the I plus j that appears in the calculation of each of your cofactors. Really, this is going to be one of 2 values all the time, right? It's always either seems to be 1 or negative 1. So let's just spell that out. So negative 1 to the I plus j is just going to be 1 in the case where I plus j is even, right? Because if it's an even power of negative 1, the result is just going to be positive 1. But if I plus j happens to be odd, then the result is going to be negative 1. Okay, so that's the first thing I want to point out. So really, we can save ourselves the bother of writing this down all the time and calculating these. We can just remember that, look, if you pick any row or column, the corresponding cofactor is going to have this power of -1 built into it. We can just determine its sign based on the position, because if the row plus the column is even, then that factor is just going to be +1. But if the row plus the column is odd, that factor is going to be -1. So I like to say we can just streamline the computation of these little factors inside the cofactors by just looking at this. I put it in quotes because it's not really a matrix, because matrices have numbers as their entry. But I'm going to make up a kind of symbolically it's like a matrix, but it's really more. You could just, if nothing else, if you want to think about it casually, just think about it as a chessboard or like a checkerboard, where you kind of how a checkerboard or a chessboard will alternate between white and black squares, right? So just think of the same thing, but between plus and minus signs. So start with a positive sign in the top left corner, and then alternate after that. So the next one down will be a positive, or pardon me, a negative, then a positive, and then a negative, and it just keeps on going forever. And then same with the first row. I start with a positive, and I go negative, and I go positive, and negative, and so on, right? It just keeps going with that same pattern. And you kind of end up creating this chessboard pattern where the symbols just alternate. And it keeps on going as long as you need it to. And you can just use it to figure out what those powers of -1 will be. So for example, here's what I mean. Consider this matrix A. When we did cofactor expansion along the first column, each one of the terms corresponded to one of these entries. So look at the term that corresponded to the entry 3. That was over here. Well, the power of -1 ended up being +1. Think about that 3 and how it relates to this matrix here. It would be occupying this position, which is a positive position. And that's why this power of -1 ended up being positive. But then the -2, that corresponded to this term down here. So the cofactor that corresponds to this entry is calculated in here, and its factor, which is the power of -1, ended up being negative, right? That's because the -2 really occupies the position that would correspond to this minus sign. And then the 5, well, the power of -1 for the 5 was +1, right? And that's because the 5 really is occupying this position. So when I say you can, and by the way, when I say you can draw this matrix as big as you like, I really mean it depends on the case, right? And in this case, it's a 3 by 3 matrix. So really, we would only need to draw this much of this plus and minus table to get what we need. Right? So that's one of the ways you can streamline some of these calculations, and just remember that there's a +1, a -1, and a +1 corresponding to the position of these 3 entries that occupy the column that we expanded along. Okay, I'll mention more about that when we get into the next example. Another remark I want to use or mention, and here's another trick you can use to save some time. Notice that when we did cofactor expansion along the first column, all 3 of the entries in the first column appeared as factors of the term. The first term had a factor of 3, the second term had a factor of -2, which is the second entry in the column, and then the third term had a factor of 5, which was the last entry in the column, right? All 3 of those entries in that first column appeared as these 3 factors. So guess what's going to happen if you pick a row or column that has a couple of zeros in it? Some of these terms are going to disappear completely. Imagine how much easier it would have been, let's say, if this whole middle term would have had a 0 here. Then we wouldn't even have needed to compute this, right? It wouldn't even matter what this evaluates to. If there's a 0 multiplying onto it, the whole term would have disappeared. Same with this one. So quite often that will be another strategy. Because remember, on the previous page we talked about this. The reason that this worked as a definition for determinants, where is it? Here we go, is that the cofactor expansion of a matrix A along any row or column is always going to yield the same result. So you have the freedom to choose a row or a column that suits you best. So in this case, we could have chosen the first row or the third column, and one of these entries would have been a 0, which means we would have only had to compute 2 terms like this instead of 3. So that's another source of time saving that you can come up with.